Okay, guys, so warm welcome for everybody here. I'm really happy that so many of you came actually. I didn't expect so many people because usually half of the people come to the meetup, but it's like somewhere around like 50, 55, 60 people, so I'm really happy about this. So we have two presenters today. First, Antal Jakovac. He was a teacher at Elta, and he's a physicist actually, and also worked abroad, like at CERN lab in Switzerland. And he will talk about understanding. So I think I looked your slides, looked around a little bit, and yeah, it looks good. So I think that will be an interesting presentation. And the second presentation is actually will be held by two people, Nora and Valer, and they are working at a healthcare startup. Yeah, called Spicy. But yeah, more about that later. I think yeah. Antal, we can start. The stage is yours. So.
Yeah, okay. So thank you very much for coming. And it's really an honor to be here and to speak about this topic. It's not actually, maybe not fits very well to the original goal is to the reading seminar. It's something which I think that can be the future of or at least one of the possible directions of future of the AI. So understanding, this will be the topic. So let's start. Okay, I think it's how can I move on? Chuck,
I don't know. Oh, wait a minute. I know why. Now, please try it. Yeah.
Okay, that's right. So these are my outlines that I would like to speak about. So first I would like to go through some introduction, and there are some mysterious titles. I intentionally left them mysterious. Facts are facts. It will turn out what does it mean. Definition of understanding, this is the next point. Next is how to solve AI task easily. The next will be, I will speak about the science of image classification, and finally about lessons and consequences. Maybe I'll go to full screen control, no, it is not. Okay, I won't go to full screen. Actually, it's almost full screen. Yeah, right. So introduction. So first question is, of course, that why to bother to understanding? It seems like an academic question, after all. And I would like to give some arguments to you that's why I think that it is a very important and crucial point to understand what we really mean on understanding. So this is the first list of arguments that meaning that AI developed a lot recently. It's true, but it faces still exciting challenges. Let me say in that way. And let's go through some points. So we mostly do supervised learning. And we all know that it needs very lot of annotated data, and it's very hard to get annotated data or good annotated data. And on the other hand, we know that humans can learn almost from one example, which is, one can discuss that in how much extent is it true, in what sense is it true, it's a question, but seemingly one can generalize from one example as also humans. Also true that humans do mostly unsupervised learning, and we have some unsupervised learning techniques, but it is not, well, it's still developing, let me say that. The next point is also very interesting, that deep neural networks used to fail in an unpredictable way. And this is, of course, a big problem for a lot of applications, for example, for the bank sector, for the finance sector, because how can a trader trust a model, trust millions of dollars if it can fail in an unpredictable way? The next point is that I like this point very much, that when we do classification, there is no I don't know category. We can approach it, but explicitly there is no I don't know category, because it would need to prepare for the unknown. And it's a hard task, that how to teach something which I don't know what will happen. Backpropagation, everybody uses backpropagation, of course, but it is problematic for very deep neural networks. It's also true that that there are developments in this field, but still it is a problem. And actually, we do not understand what are the different layers do in a deep neural network. So the question is that whether there exists an interpretable deep neural network or not, and so on and so forth. So everybody can list their own problem. So it's really AI or deep learning faces exciting challenges. It's just okay, I didn't make it in the English, but anyhow, so this is the classification errors. I've collected some of them, which shows very well, that's very nicely, that there are still a lot of things to do. And there is another point. If anybody here had a teaching experience, but everybody has a student experience, there is a subtle difference between being trained and understanding something. So we know very well that pupils like to do that, learn the answers to the questions, and then in the exam, when they have to give an account for their knowledge, they will know the answers to the given questions, but it is not the same when they try to generalize the knowledge. So it's a very subtle difference between the two. And nowadays we train our networks, but we would like that the network would understand the system somehow. And for that, because of this subtle difference, it's very important to understand the mechanics of understanding itself. So this is the next motivation slide. So let's try to approach the topic nice and easy. So what is understanding? First, what can we understand? We can understand a lot of things, a math formula, a book, a joke. This is the everyday sense of understanding. To be more quantified, we want to know if we understand the topic or not. And usually what we do is that we pose questions. We pose questions to the students, we pose questions to ourselves to know that if we know the topic well enough. But these kind of questions which occur in the human communication, we can control questions, for example, that please choose the rational numbers from the following list. We can ask for a computing question that asks what is the slope of this line, compute the slope of this line, for example. Summarizing questions that, for example, write shortly the content of the War and Peace shortly. We can ask for an example that, for example, tell an example for an exothermic reaction, and so on. And it's very funny that these are the same tasks that we pose for AI as well. This corresponds to classification, regression, compression, summarization, and decoding problems, tasks of the AI. And so there is a technical definition of understanding that which actually stems from Dirac. He's a famous English physicist. That we should find a description of a phenomenon where all of the above tasks can be easily solvable. So easily, it's not a very much. So it's not a quantitative thing, but everybody knows that what means easily, and I will show that. Indeed, if we do it correctly, then we can answer them very easily. Another problem with understanding is that the understanding is not unique. So we can understand the subject in several ways. For example, if we ask that what is on the picture, then the answer will depend on to whom we ask it. For a computer, or somebody who digitalizes this picture, he or she will say that there are pixels on the picture in different colors. For a painter who wants to paint this picture, this image, for the painter, it contains of textures, colors, patches, and so on. So all of the things related to how to paint this picture. For an external observer, it realizes something. Realizes a cat, a woman, a curtain and background, and so on. And then for an art dealer, neither of them. For an art dealer, this is Renoir, the woman with a cat picture. So it's again a different answer. And all of the answers are correct. So we cannot tell that understanding is one of them. No, understanding any of them, and we have to be able to give an account for all of these answers that show up here. So they're all like legitimate understandings. And it's also very interesting that they do not follow from each other. So this is, sometimes people think that from a microscopic understanding, we will know the macroscopic understanding. It is not true in this example. We cannot tell, knowing the pixels, that it is Renoir, one woman with a cat. It's very, very far, very, very too far from each other. So it's kind of question of a hardware and software. If we know the hardware, we cannot tell what kind of software runs on it, and vice versa. That we know that I have a Windows on my laptop, then I don't know what is the type of my laptop. So these are other understandings of the same topic. So we also have to give an account for this problem. So let's start. Facts are facts. In Hungarian, it's the tények makacs dolgok. So understanding, of course, have to be based on facts, but there are infinitely many facts. Of course, so everything is a fact. That the wall is white. It's also a fact. So the question is, how can we organize the facts? And to understand that the organization of the facts, we should perform a simple physical experiment. Actually, a physical experiment is an abstraction even itself, but everybody knows what I'm thinking about. So here balls colliding ideally, so without loss. That means that we started a ball up here, it goes down, collides with a black ball, and the black ball will fall eventually after some time, and we measure the time of falling down. So this is the time where from the collision to the fall down. And what we do is that we perform many experiments with different circumstances, with different balls, different height, different colors of the balls, different experimenter, different wall colors, and so on and so forth. And what turns out is not all the facts are the same important. It's just only a few will influence substantially this delta t. And we can, of course, compute it because it's not a big challenge. So actually, it turns out that there are three facts that influence importantly this fall of time. And these are T0, M, and small and large, and the mass of the two balls, and some combination of the H and S. Okay, what can we learn from that? What we can learn is that the facts are not equally important. Everybody knows it, but anyhow, let's just go through these steps. So there are important facts or features or notions or concepts and anything can be used that are important to describe an experiment, and these we will call relevant concepts, very relevant notions. And there are a lot of other notions that are not relevant, so they are irrelevant. For example, in chemistry, the relevant concepts, notions are, for example, the atoms, molecules, atomic orbits, binding energy, reaction, and so on, concentration, and so forth. Usually these concepts are not necessarily independent, and if there are always valid connections between the relevant facts. So we always speak about the relevance concept now. So if there is always valid connections among the relevant facts, then we can call it low. And but there can be relations which are valid only in a given subsystem. For example, a ratio of excitation levels of a given molecule, and this is just a relation. But usually these concepts are not independent. Okay. So what we see, we just go back here. So probably there are, for example, here we have more relevant quantities than just what appears here, because we could measure S and H separately, but there is only one combination which appears in this picture, in this equation. So this means that these facts are not independent. So I think we can now define understanding, and I use some math for it. I hope that it will be followable. So, for example, to start with, let us assume that we know all the details of the system. So we know every detail which is important. If, for example, if we have a big picture on a computer, we really know every pixel. So it's not a weird assumption. And from them, we can form a state space, which is an n-dimensional real vector space. So all details in this picture can take a real number, or can be characterized by a real number. So we have an n-dimensional real vector space. For example, if we have n particle piece of particles, then their state can be characterized by the phase space. That means their positions and all the velocities. It's a 6n particle dimensional real vector space. On a computer image, assuming that all colors are real numbers, which are not, but anyhow, in this case, we assume that, then the number of the dimension of this vector space is 3 times nx times ny. Okay. But it is not compulsory that we use the original degrees of freedom, the original characterization. But we can change characterization very easily. Technically, it happens that we define some mappings or measurements or observations which maps a state to a real number. And then we can collect all of the mappings. It's a very huge space, of course. But then we can form a basis from them, which goes from the vector to the state space to r to the n, so n real number, which should be a bijection at least locally, and also invertible locally. And in this basis, we can also represent a state, not only in the original state or original characterization. Let's look at some examples. For new bases. For example, a very simple two-dimensional example is the polar coordinates, when instead of x and y coordinates we use an angle and a radius. This is a good change of basis. Another change of basis can be encountered when we describe colors, because the colors can be described in RGB, so red, green, blue frame, the HSB frame, the hue, saturation, and brightness frame, or CMYK. These are just different coordinate systems for the same stuff. We can have different image formats and so on. So the point is that all the information is there, only in a different format. This is the point. All the information is there, just in a different format. And of course, very exotic coordinate system is conceivable, especially if we have a very, very huge space. Okay, but usually we are not interested in anything on the picture. So we have some interesting subsystem. So we do not want to take into account all the details. And we can define observable quantities. this is not, it means that we can observe, but we want to observe these quantities. We are willing to observe these quantities. These are mappings from the state of the system to a real number. We measure it. Now, for what is an observable quantities? In physics, for example, we do not observe atoms when we look around. We cannot observe actually atoms, but we don't bother when we would like to describe a motion of a rigid body. We do not bother to describe atoms. That means that the observable subsystem is really what we can measure macroscopically, like on the picture there. But in the case of a computer image, we can tell that, for example, we just want to tell what kind of species of animal is on the picture. This is the observable subsystem, and we don't bother that whether if it is a cat, then it is standing or lying or what he or she does. Okay, now so that means that we have a subset of all the observations, which are important, interesting for us, and using this subset, we can speak about equivalent states. This will be the classes in the image classification, the equivalent states. So two states are equivalent if any of the elements of the observable subsystem gives the same answer to them. So this is how we can, this is called equivalent subsystems. For example, all the pigs with cats are from this point of view are equivalent, because or observable quantities contains just the species of the animal. Okay, so they cannot be distinguished by any observable quantities. So and these will be the classes of in the classification task. So, and now comes the definition. I don't know how much it is natural for you, but I will prove that it will be a good definition. That we will do the following: that we choose a basis from this F observable subsystem. So we take all of the observable things which we can imagine, which we are interested in, and form a basis from them. For these are independent functions. So these are coordinate system, but only in this F observable subspace. It is of course not unique. We can choose the Descartes coordinate system or polar coordinate system is the same. This is not unique, but the point is that it is basis in F observable. And then we extend it to be a basis in the complete space. So, but these are, of course, these are observable, these are not observable stuff. And what my claim is, so the last and large n minus small n elements are not observable. And my claim is that understanding is to find this function, this coordinatization. Okay, let's look at how it works, because it's not necessarily very natural. So if we have this knowledge, how can we solve AI task easily? This is the question. Okay, first of all, how can we find the laws? The natural laws, which actually big data word is so much desperately wanting to find some new natural laws of nature. If we have this coordinatization, it's very easy, because any elements of F observable can be, let this be G, so it's a relevant quantity. Then since it's a bijection, it has an inverse, and so it's a unity, and then we extend it according to this above rule. So first n, the small n is the observable stuff, and the rest is the non-observable. And since G is observable, it doesn't depend on these coordinates, so we can put them 0 for them, and then we have a functional relation, which is a law. This is the natural law, Newton's equation, for example. Okay, let's go on. And, let's go through this shortly on the test questions we have posed to check if whether we understand the stuff what we want to study. First question, it was the control question. Now, what we can tell that the distinguishable states are differ only in the value of the at least one of the relevant quantities from this. So as I've said, this single out the classes in the classification. Okay, that means that the classes are corresponds to definite values of the relevant quantities, and therefore for a control question for classification, we have to take into account only the relevant quantities because they define the classes. So if we have this coordinatization here, okay, I don't know, I don't see myself at that point. So if we have this coordinatization, we have to just concentrate on the first n quantities, and then we can find the classes. Okay, this is for classification. What is regression? Now, the regression is just the other part, because in regression we already defined the class. So we want to be within one definite class. For example, we are in the class of all straight lines. And we just want to know the details of this class. So just it is the reverse question, since the relevant coordinates are fixed by the question, and we just want to know the irrelevant ones, the irrelevant coordinates. So this was the classification, and this the value of these is the regression. So regression, for regression we have to find the value of the irrelevant coordinates. It's just the other part of this coordinatization. Compression. What lossless compression? The lossless compression is the same, because we have a definite class. For example, we want to compress all the landscape peaks. So that means that the relevant coordinates are fixed, and it can be stored in the hardware. What cannot be stored in the hardware are the details, and this is what a compression should store in order to reconstruct the original image, for example. So for compression, that means we have to store all the values of the irrelevant coordinates. So again, this function here is again very useful in the way we can compress very easily. And let's the summarization. For summarization, we have to take into account again the relevant coordinates, but not all. We have to somehow sort the relevant coordinates and mention the most important ones. So for summarization, we have to sort the relevant coordinates and mention the ones who the teacher thinks that they are the most important. And and finally, decoding. Again, decoding, we want to have a picture in a given class. That means that we have to fix the relevant coordinates, but the irrelevants are arbitrary. So that means that we take the irrelevant coordinates randomly, choose them randomly, and take the inverse of this coordinatization, and then provides you an image, for example, which is in the desired class. So again, for decoding, we need to fix the relevant coordinates. So that means that we could really easily answer all of the questions of the understanding, which concerns the understanding. So we can rightfully say that finding this coordinatization is equivalent of understanding something. Of course, in practice, one cannot find it very easily. It's a very, very hard task, but it means the complete understanding for a given stuff. Okay, so let's try to apply it for image classification, because will turn out a very important thing. So what we have seen before I start, that we have seen that in this colliding balls experiment, we had 3 relevant coordinates. And this was T0, M, small m, and large m. And all of the others are irrelevant. That we have to keep in mind. And now let's look at the image classification. So for image classification, we can apply the same framework. Nothing changes. Actually, I've used examples for using the image classification task. So the state space, as I've said, is that a set of all pictures, for example, in the basis of the colors or any other basis. The observable subsystems, for example, are objects in the picture or the painter or anything. So you can choose the observable subsystem by your desire. So they can be, for example, if the objects are in the pictures, then cat, meat, butterfly, and so on. Equivalent states, for example, if we want to choose cat pictures like here, cat in the dark, in the light, tabby cat, Siamese cat, and so on. These all equivalent states. These are the cat pics, so to say. But okay, then we understand that. But why don't we know the natural laws of the cat pictures? Why we don't know? Why we don't understand the cat pictures? Why can't we list the relevant coordinates what we could do in this very simple experiment of colliding balls? What is the difference? And the difference is that how many relevant coordinates are there. This is the very big difference between science and image classification. Just the opposite, as you will see. Let's see a simple example. This is a 100 by 100 pixel peaks. So if it's element of r to the 30,000. And we will consider peaks with a single square, a single black square actually in this case. That means that we take into account all the peaks where in white background anywhere there is a black square, like here, what you see here. How many relevant coordinates and how many irrelevant coordinates are there? Now the irrelevant properties are so this is the class, and only 3 parameters determine the irrelevant coordinates. Where this point is and what is the side of the how long is the side of the square. So there are 3 parameters, and all of the others, the 29,000 blah 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 parameters, are all irrelevant or relevant. Or relevant. So it's just so that when in physics we had 3 relevant parameters and tons of irrelevant ones, in image classification we had tons of relevant quantities and very few of irrelevant ones. And actually, if you remember that compression is to store the irrelevant coordinates, here the compression is very easy. Actually, compression is just to remember the 3 numbers. If we know these 3 numbers, then everybody can restore the black square on the white background. Let's see another example, but it's the same actually, just a little more colored. That we have, again, 100 times 100 colored image with some rectangles, the number smaller or equal than 10, and it's a binary picture, and then we can then count the number of such images, and it turns out that the number of these images is 2 to the 486. That means that it contains 486 irrelevant bits, and all of the other bits are relevant. That means the plot, okay, to 200,000 or something like that. Again, the same. Even in a more complicated picture, the same consequences is there. So the point is that for images, the number of relevant coordinates is very large, and that's why they are compressible, and that's why they are not understandable. That's why we don't know. In this case, we just hand-tailored the relevant coordinates. So in this case, we know the relevant coordinates, but usually in a cat peaks, we don't know the relevant coordinates. There are 2 lot. And let's another example on this topic, the algorithmic image classification. So algorithm will do that. We want to find the relevant quantities, or at least the most important relevant quantities, and find their relations. This is what an algorithm does. And as I've said, that in a natural laws, in natural pictures, for example, in cat pictures, there are too many relevant coordinates, and it is very hard task to find the relevant quantities. And that's why, for example, that image face recognition, which is a very, very long-standing task from the 60s, we are still not on the position that we have a very, very good algorithmic approach. For example, if anybody knows this, Apple Face ID uses 30,000 base points, or 30,000 relevant parameters, relevant quantities, and who has this experience with that, I've read, is not, well, good, but not always very, very reliable, actually. So the bottom line is that it is very hard, or maybe impossible, to work out by hand that what are the relevant concepts for a given class of picture. Okay, I know how much time do I have. But anyhow, it's the last part of my talk about the lessons and consequences. So what we have, I hope that's what I could tell you, that an argument that what an understanding means and why natural laws of physics can be determined and natural laws of image classification cannot be determined. But how to go on? So the general lesson is that if there are not too lot of relevant parameters, and these parameters can be well defined, then there exists an algorithm. This we call a scientific approach. But if there are too lot of relevant coordinates, or these are not very well definable, for example, they change too fast, then there is no algorithm. There is no algorithmic approach, no scientific approach. And actually it somehow makes a constraint on the application of science, just in parentheses. But in general, there is a continuous spectrum of an impossible and absolutely possible of understanding stuff. For example, if we have seen that geometric forms, although they contain a very lot of relevant coordinates because it's hand-tailored, then we can understand. Face recognition is in the middle. We had put a very lot of effort, and we sort of understand what face recognition means, but general image recognition is not possible. And again, the other example is chess and Go. For chess, there are algorithmic approaches. For Go, there are no algorithmic approaches. And in scientific disciplines, from physics to art, there is a series where less and less understanding in this sense can be done. But of course, it is very hard to tell in advance that how many relevant parameters are there, and whether there won't come a very clever guy and say that, oh well, come on, this is a very simple stuff, and finds the good relevant coordinate. But anyhow, this is one message which I wanted to tell you. The other question is that, okay, we know that why is general understanding is not possible, at least by hand-made, hand-tailored characterizations. But why is artificial intelligence does better? So an intelligence doesn't want to tell before the relevant coordinates. They want to somehow find out experimentally through examples. And that's why in artificial intelligence a much more refined characterization is possible. And we know different techniques which nicely fit in this framework. For example, in the Bayesian approach of classification, we assign one relevant quantity for each classes, and these coordinates are interpreted as probabilities, as probably you all know. In the case of autoencoders, so here there is one relevant quantity for each class. For autoencoders, there is a multi-dimensional internal space, or a multi-dimensional coordinate space is there, and which these are the relevant coordinates actually in the middle of an autoencoder. So it can be that's why it is good for compression or a generalized regression. But in the ecosystem, the evolution of the species, there also it can be interpreted as intelligence, because somehow the species find the relevant coordinate of the environment. And in this case, besides of evolution, there is an other strategy, and this is adaptation, which I think can be very useful when one goes on with this to develop AI. And the final slide is that is there any consequences of this, what I've told? The question is there a strategy that fits best to the previous concept of understanding? And I think is that maybe the most important message is that what I think is that learning is not about goal-oriented training. Instead, we should think about it as a feature or concept extraction. And for example, from this point of view, it's not enough to characterize a class with a single coordinate. At least some 2, 3, 4 independent coordinates should be used to characterize a class. And okay, this is not too important. So I think instead of backpropagation and adaptation is better, but it's not so interesting. But so I think it's time to stop training and start understanding in the case of AI. Thank you very much for the attention.
Okay, guys, what questions you have?
I mean, if you observe the feature space of like the raw dimensionality of an image like RD, a huge set of possible pictures, but actually I think what turns out that the eventual pictures that you can observe at all during the course of the universe is in a very small manifold inside the thing. So maybe one of the takeaways here is that if we observe only the raw coordinate system that is given, it's not the effective description of that phenomenon.
Sure.
That is just description length.
Exactly. So the subspace is constrained by the relevant coordinates, and that exactly what you say. That it's a very low dimensional subspace. That means that very constrained subspace, and this is because there is a lot of constraints. There are a lot of relevant coordinates. Exactly.
But on the other hand, I think the disturbing fact is that relevant coordinate in conjunction or in regard to a certain classification or a certain question. Yeah. So I think enumerating all the possible coordinates or all the possible features that would be interesting for a decision would mean that there is a finite set of decisions that you can enumerate and want to take, which is, I think, the real problem here. Is that you cannot go on for what are the things that you want to classify for. So, though it is a small manifold, but the description length is not finite.
Yeah, that's why I think that, so the ideal would be to find a lot of relevant quantities, but at least more than one. So the today classification, my problem with the today classification is that anybody trusts one. A cat is the thing, the property which is most catty, and so on. And I think it's not enough. And,
more like the unsupervised approach, where you would like to have a good general description of the phenomena and use the general description as a classifier input.
Okay. Any other questions? Yes.
Actually, the topic you are addressing is about reasoning, while either it's inductive or deductive. And in physics and other sciences, it's obviously inductive. So all the laws are known. You want to estimate the parameters.
Right.
And if you repeat the experiment hundreds of times, you will still have the same results.
Yeah.
But in real-world data, you will learn from the data by example, as you mentioned, and this is deductive, where you have to choose the best example to learn from. However, there is a third way to do it, which is abductive. It's like when you go learn second language, you learn some certain sentences, and also you learn grammar. So, which that you learn from data, and you add some more constraints to your learning, and this may be faster to do that. And that's why one of our research in the university, we want to have a conditional autoencoders that the latent space is two parts. One is like from a transformation of the data, and the other is learned by the reconstruction error, backpropagation.
Mm-hmm.
And what is the question?
No, he did mention the abstraction, the abduction third way that mixed two. He's focusing on the feature abstraction.
Okay, let me comment something about that. I agree that in the learning it would be there are two ways of learning. So, but what is missing from the, for example, in deep neural networks is the structure. What you have said, the grammar, that which is somehow algorithmic. We know we take it from our earlier language, from our mother tongue, and somehow we should implement it for a new language. And I think it's a very important question. I don't know the answer, and I don't know how can they, but definitely to take some structure from the earlier knowledge, structured knowledge would be very important for AI, for the future of AI. So
like an inductive bias, you think?
Yeah.
Any other questions?
You mentioned that the regression task is about irrelevant parameters, and I think you can also find relevant parameters for the regression question, because your original example about the bouncing balls, it's more like a regression question, what time it will hit the ball, or it will
Well, what is relevant and irrelevant here is it depends on the question, but the framework. What you, for example, so okay, we can discuss it. But what is the slope of this curve? That means that we take all the curves. I mean, all the straight lines, and from that we choose one and we want to decide very exactly what is chosen. If you like that. Okay, in this case, there are three relevant parameters, the T0 and small and large m, and maybe H and S can be taken as independent stuff. And in this class, it is indeed a regression question. But if you define the class with these parameters, then this is a regression, which is actually turns out to be a law or a fixed relation in this system. So it's a little bit dependent on the point of view you apply.
Any other questions, guys? Okay, so then let's have 15 minutes of break, and then we will continue with the second presentations, okay? So at 30, okay? 7:30, we continue. Thanks.